Welcome to Deep Learning series. This is an video on Advanced TensorFlow framework. Before we start today's topic, let me tell you that this video is part of Deep Learning series, which we have started after we got a lot of requests from developers who watched our earlier web series on machine learning. It was a 6-part video series. Now Deep Learning series will be a web series with major focus on development and implementation of deep learning frameworks rather than earlier machine learning series where we just understood and revised the artificial intelligence concepts without going much deeper into the topics. So let's start the deep learning series second video, and today's topic is advanced course of TensorFlow for deep learning and cognitive computing. We'll be exploring various components of TensorFlow and its ecosystem, and we try to explain few important concepts, namely how it is compatible with latest deep learning concepts, how a programmer can be a data engineer using TensorFlow. Finally, we end this video with some of the latest features of TensorFlow 2.0. So let's start the fabulous, fantastic journey of TensorFlow and its evolution as dominant player in deep learning ecosystems. As every beginner starts with a curiosity to know what is TensorFlow and what is so interesting about it, which is drawing every IT specialist from all over the world towards it. Probably a beginner in deep learning also wants to become an expert of deep learning. Keeping all these points in mind, we will focus on first few videos of the series on upskilling the developers with tips and programming techniques of popular deep learning frameworks, so that we bring the viewers to prerequisites of advanced deep learning and cognitive computing. First among list of deep learning frameworks is TensorFlow, so we'll explore TensorFlow in this video. Open source community has defined TensorFlow as follows. TensorFlow is an open source software library for numerical computations using data flow graphs. Maybe now you would be curious to know why TensorFlow is called TensorFlow. Because it is a data flow language and deals with data stored in multidimensional arrays, also known as tensors. TensorFlow starts the numerical computation with construction of flowchart of operations called data flow graph, and then tensor flows through this graph system which applies multiple operations of a given deep learning algorithm. Hence the name TensorFlow is derived using tensor and data flow. It is used for both research and production at Google and at various artificial intelligence service providers. Now I briefly let you know about how it evolved from Google and some of its key features. TensorFlow was developed and launched at Google in 2015 under the Apache 2.0 open source license. It started as a prototype project by Google Brain team inside Google Machine Intelligence Research Organization. Starting in 2011, Google Brain built Disbelief as a proprietary machine learning system based on deep learning neural networks. Its use grew rapidly across diverse alphabet companies in both research and commerce application. Google assigned multiple computer scientists, including Jeff Dean, to simplify and refactor the codebase of Disbelief into a faster, more robust application-grade library, which became TensorFlow. TensorFlow helps deep learning developers by providing primitives for defining and training functions on tensors and automatically generate their derivatives. TensorFlow is complemented by high-level Keras API. TensorFlow provides stable Python and C APIs as well as non-backward compatible framework and APIs for C++, Go, Java, JavaScript and Swift programming language. This was simple introduction for TensorFlow. We'll now delve deeper into this framework and further into its ecosystem as we move ahead in this video. So why TensorFlow? What is making most deep learning programmers prefer TensorFlow as their first choice? As you can see in the Google's recent trends, TensorFlow tutorial is the most searched term among deep learning enthusiasts worldwide, and the graph is still climbing. It only indicates that it has some more good years ahead in deep learning domain of IT industry because of its good features like well-documented stable Python API. TensorFlow framework is highly portable, that is, it can compute the deep learning algorithms on various devices and neural networks. It has got good flexibility of executing programs in different modes like eager execution and deferred execution. It has got a very good visualization tool popularly known as TensorBoard. TensorFlow has good and easy debugging and development utilities, and with inline checkpoints within programming modules or packages. Autodiff, that is no more taking derivatives by hand, it automatically computes for its tensors. TensorFlow has got a large dedicated open community delivering a very stable, robust deep learning framework. Large community in the sense it has more than 10,000 commits and more than 3,000 TensorFlow related repos in 1 year of launch. Some of the awesome features of TensorFlow extensions are as follows. TensorFlow extensions help developers automatically add operations to calculate symbolic gradients of variables with respect to loss function. TensorFlow extension help developers apply these gradients with an optimization algorithm very easy. TensorFlow extension help developers launch the graph and run the training operations in a loop. There are many high-level APIs built on top of TensorFlow. Some of the most popular APIs include Keras, TensorFlow Learn, PrettyTensor. However, the primary purpose of TensorFlow is not to provide out-of-the-box machine learning solutions. Instead, TensorFlow provides extensive suite of functions and classes that allow users to define models from scratch. This is more complicated but offers much more flexibility. You can build almost any architecture you can think of in TensorFlow. I hope by this time you would have got better picture about TensorFlow, and my previous slides of TensorFlow would have kindled interest in it. So let's list down the prerequisites of deep learning for a developer, as this is one of the important information everyone should be aware of. Also, deep learning has become an ocean of knowledge with a huge learning curve, which also includes interdisciplinary skills from streams of mathematics, statistics, and computer science. So let's elaborate it properly. Some of the essential skills for a deep learning TensorFlow developer are as follows. Firstly, proficiency in programming basics and some experience coding in Python. That means one should have a firm understanding of Python and the Python ecosystem. Have a hands-on programming exercises in machine learning. It would be really handy if you have completed a crash course in Python using TensorFlow. No prior experience with TensorFlow is required, but you should feel comfortable reading and writing Python code that contains basic programming constructs such as functions, definitions or invocations, lists and dictionaries, loops and conditional expressions. Secondly, machine learning developers should be aware of linear algebra, real analysis, differential calculus. So a developer should be having a mastery over topics of statistics like basic statistics, correlation and covariance, exploratory data analysis. Also, he should have good grasp of the most important modeling and prediction techniques. Along with relevant applications, the other statistics-based topics include linear regression, classification, resampling methods, shrinkage approaches, tree-based methods, support vector machines, clustering, etc. Thirdly, developers should have introductory and hands-on knowledge of exploratory data analysis, which is a key preliminary step in data science, and then if he has knowledge of big data techniques, which is optional, it will be good. As a data analyst or a data engineer, he should be able to understand how the principles of experimental design yield definitive answers to questions, how to use regression to estimate outcomes and detect anomalies, and also he should understand key classification techniques for predicting which categories a record belongs to. Fourth, developers should be aware of topics of machine learning like statistical machine learning methods that learn from data, unsupervised learning methods for extracting meaning from unlabeled data. Also, developers should know what are artificial neural networks. Since we are in deep learning video, before we start with the prerequisites of deep learning, I would like to explain very briefly about artificial neural networks. Neural networks is made up of neurons. Neuron is simplest building block of neural network. A neuron receives a signal, processes it, and propagates the signal. The brain is comprised of around 100 billion neurons, each connected to an average of 10,000 other neurons. Each have neuron having 10 to 15 synaptic connections. So, artificial neural networks are a simplistic imitation of a brain comprised of dense net of simple structures like neurons. I hope it refreshed a bit of neural networks concepts. Now moving to deep learning prerequisites. A TensorFlow developer should be having mastery over introductory topics of basic deep learning like feed-forward neural network, convolution neural network, recurrent neural network, multi-layer perceptrons, optimization algorithm, computational performance, computer vision, natural language processing, generative adversarial networks. Softmax function is the most common used operation in deep learning. Softmax function calculates the probabilities distribution of the event over n different events. The main advantage of using softmax is the output probabilities range. The range will be between 0 to 1 and the sum of all probabilities will be equal to 1. If the softmax function used for multi-classification model returns the probabilities of each class and target class will have high probability. In mathematics, the softmax, also known as soft argmax or normalized exponential function, is a function that takes as input a vector of k real numbers and normalizes it into a probability distribution consisting of k probabilities. That is prior to applying softmax. Some vector components could be negative or greater than 1 and might not sum to 1. But after applying softmax, each component will be in the interval of 0 to 1 and the components will add up to 1 so that they can be interpreted as probabilities. Furthermore, the larger input components will be correspond to larger probabilities. Softmax is often used in neural networks to map the non-normalized output of a network to a probability distribution over predicted output classes. So softmax function can be written as
the standard unit of softmax sigma is Rk implies Rk is defined by the formula sigma of zj is equal to e to the power of zj whole divided by sum of e to the power of zk, where k starts from 1 to k, for j is equal to 1 to k and z is equal to tuple of z1 up to zk is an element of Rk. Properties of softmax function are as follows. The calculated probabilities will be in the range of 0 to 1. The sum of all the probabilities is equal to 1. The softmax function is used in building neural networks. Softmax function is used in different layer levels inside neural networks. Hope you got a fair list of prerequisites to be aware of. Now let's explore some cool, awesome projects developed using TensorFlow. First one is Neural Face. Neural Face is an artificial intelligence library which generates face images, and all images in this slide are not real. This project is a TensorFlow implementation of Deep Convolution Generative Adversarial Networks DCGAN, which is a stabilized version of Generative Adversarial Networks GAN. As you can see in the image with title Neural Face is data set of Asian faces having all the human emotions, which was completely generated using deep learning algorithms called DCGAN TensorFlow. Neural Face is implemented with TensorFlow and GTX 980 Ti, which was trained for 2 days. Below is a series of images generated by generator with a fixed Z between first and the fifth epoch of training. The vector z has real values from -1 to 1, and it follows the Gaussian distribution. We can see the most common phase that is interpreted by neural phase using 0 as all values of z. Another image was generated by changing 10 different values of z from -1 to 1. People in the images vary in characteristics such as smiling, wearing glasses, turning into black and white images, and changing into different sex. So after 6th epoch, you would see the below different set of generalized faces. And the URL for the repository in GitHub is http://carpetm20.github.io/faces. This URL is also given in the description below. The second project is TensorKart. It's a self-driving Mario Kart game implemented using TensorFlow. In this TensorFlow project, TensorKart, a convolution neural network CNN was trained to map raw pixels from a single front-facing camera directly to steering commands. It used Adam optimizer along with L2 normalization and dropout algorithm for training. The program used an OpenAI chip environment wrapper for the MuPen64 plus N64 emulator to execute the trained agent against the Mario Kart environment. The environment will provide the screenshots of the emulator. These images will be sent to the model to acquire the joystick command to send. This end-to-end approach proved surprisingly powerful. With minimum training data from humans, the system learns to drive in traffic on local roads with or without lane markings and on highways. It also operates in areas with unclear visual guidance such as in parking lots and on pavement roads. The URL of this repository is https://github.com/kevinhughes27/TensorKart. The URL is given in the description below. Third project is Sonat. Sonat is a library built on top of TensorFlow for building complex neural networks. The framework provides a higher level of abstraction for the construction of neural networks based on a TensorFlow computation graph. The main principle of Sonat is to first construct Python objects which represent some part of neural network and then separately connect these objects into TensorFlow computation graph. Models that have been written in Sonat can be freely fixed with raw TensorFlow code. The objects are subclasses of Sonat.abstract module and as such are referred to as modules. Modules may be connected into the graph multiple times and any variables declared in that module will be automatically shared on subsequent connection calls. Sonat modules once constructed follow the tensor in tensor out principle, so can be mixed with functions from TensorFlow Slim, etc. The paradigm of separating configuration from connection also allows easy composability of modules. The existing libraries were judged insufficiently flexible for the DeepMind use case, where extensively use is made of weight sharing, making everything use of function tf.make_template and therefore support weight sharing from the start seem to have sufficient benefits to outweigh the development cost. Modules can be combined using arbitrarily complex models, and Sonat enabled developers to build their own modules using a simple programming model. An additional advantage of representing modules by Python objects is that it allows additional methods to be defined wherever necessary. Here are some of the favorite benefits deep learning developers got from using Sonat in their project. Benefit number 1. Neural network training. Sonat simplifies training of neural networks by focusing on individual modules. Benefit number 2. Testing. Sonat's higher-level programming model simplifies the automated testing of neural networks using mainstream frameworks. Benefit number 3. Extensibility. Developers can easily extend Sonat by implementing their own modules. They can even control the construction of TensorFlow graph related to that module. Composability. Imagine having access to an ecosystem of built and trained neural network modules that can be dynamically composed into higher level networks. Sonat is certainly a step forward in that direction. Benefit number 4. Composability. Imagine having access to an ecosystem of built and trained neural network modules that can be dynamically composed into higher levels. Sonat is certainly a step forward in that direction. Benefit number 5. Multi-neural network application. Implementation of multi-neural network solutions such as multi-layer neural networks or adversarial neural networks in TensorFlow is something short of a nightmare. Sonat's module programming model can help to implement individual neural networks that can be combined to implement higher level networks. Finally, Sonat supports the virtual environment installation mode of TensorFlow as well as the native pip installation mode. Sonat is the latest addition to the stack of DeepMind's open source.
Coming to fourth project, it is beautiful, awesome project for the fine art lovers. We are talking about how to convert our normal photos getting stylized into very famous modern art paintings using fast style transfer project, which is developed using TensorFlow. This project is based on the following 3 deep learning papers. Number 1, a neural algorithm of artistic style by Leon A. Ketze, Alexander S. Ecker, Matthias Bethig. Paper is available on https://arxiv.org/abs/1508.06576. Please forgive me if I have mispronounced the names, and the URL for this paper is given in the below description. Second paper, Perceptual Losses for Real-Time Style Transfer and Super Resolution by Justin Johnson, Alexandria Alahai, and Lee Fei. Paper URL is https://cs.stanford.edu/people/jacobs/papers/eccv16.pdf. The URL is given in the description below. Third paper is Instance Normalization, the Missing Ingredient for Fast Stylization by Dmitry Ulyanov, Andrei Vidaldi, and Victor Lemtisky. The paper URL is https://arxiv.org/abs/1607.08022. The URL is given in the description below. Fast Style Transfer in TensorFlow. This project adds styles from famous paintings to any photo in a fraction of a second. You can even style videos. The resulting method can be used to train high-performance architectures for real-time image generations. This implementation uses TensorFlow to train a fast style transfer network. We use roughly the same transformation network as described in Johnson's style transfer network mentioned in the paper number 2, except that the batch normalization is replaced by Ulyanov's instance normalization, and the scaling or offset of the output tan H layer is slightly different. We use a loss function close to the one described in Gatti's using VGG19 instead of VGG16, and typically using shallower layers than in Johnson's implementation. Example, we use ReLU1_1 rather than ReLU1_2. Empirically, this results in a large-scale style features in transformation. It takes 100 milliseconds on a 2015 Titan X to style the MIT Stats Center of the resolution 1024 into 680 pixels, like Udini by Francis Picabia, as you see in the slide. The GitHub repo URL is given below in the description. Is https://github.com/langstorm/faststyle-transfer. Langstorm team for this project consider the image transformation problems, where an input image is transformed into an output image. Recent methods for such problems typically train feed-forward convolution neural networks using a per pixel loss between the output and the ground truth images. Parallel work was shown that high-quality images can be generated by defining and optimizing perceptual loss functions based on high-level features extracted from pre-trained networks. They combine the benefits of both approaches and the use of perceptual loss functions for training feed-forward networks for image transformation tasks. Fast style transfer show results on image style transfer, where a feed-forward network is trained to solve the optimization problem proposed by Gatsby et al. In real time. Compared to the optimization-based method, fast style transfer network gives similar qualitative results but is 3 orders of magnitude faster. Langstorm team also experiment with single image super resolution, where replacing a per pixel loss with a perceptual loss gives visual pleasing results. The instance normalization, the missing ingredient for fast stylization paper by Dmitry Ulyanov. The Langstorm team revisited the fast stylization method introduced by Ulyanov et al. And Ulyanov et al. Showed how a small change in the stylization architecture results in a significant qualitative improvement in the generated images. The change is limited to swapping batch normalization with instance normalization, and to apply the latter both at training and testing times. The resulting method can be used to train high-performance architecture real-time image generation. The code is made available on GitHub at https://github.com/dmitryulyanov/texture_nets. The full paper can be found at arxiv.1701.02096. The URLs are being given in the description below. The third paper, Improved Texture Networks, Maximum Quality and Diversity in Feed-Forward Stylization and Texture Synthesis, is the recent work of Gatiels et al., who characterized the style of an image by the statistics of convolution neural network filters, ignited a renewed interest in the texture generation and image stylization problems. While their image generation technique uses a slow optimization process, recently several authors have proposed to learn generator neural networks that can produce similar outputs in one quick forward pass. While generator networks are promising, they are still inferior in visual quality and diversity compared to generation by optimization. In this work, Gatsby et al. Advance them into 2 significant ways. First, we introduce an instance normalization module to replace batch normalization with significant improvements to the quality of image stylization. Second, Getz et al. Team improve diversity by introducing a new learning formulation that encourages generators to sample unbiased from the Jules's texture ensemble, which is equivalence class of all images characterized by certain filter responses. Together, these 2 improvements take feed-forward texture synthesis and image stylization much closer to the quality of generation via optimization, while retaining the speed advantage. So basically all the 3 mentioned papers, image transfer principle algorithms, were used to implement this fast style transfer project for stylizing the photos into visual appealing modern art. I have shared the links of the paper in the YouTube description below for further details and for your reference.
The 5th awesome cool project using TensorFlow is Speech-to-Text WaveNet. Speech-to-Text WaveNet is an end-to-end sentence-level English speech recognition library based on DeepMind's WaveNet and TensorFlow's framework. This project used the free VCTK voice cloning toolkit dataset instead of using single CTC loss because VCTK provides sentence level labels. As a result, we used only dilated Con1D layers. We extracted
MFCC null frequency substral coefficient features from wave files and remove the final mean pooling layer because the original setting was impossible to run on Langstrom's Titan X GPU. Finally, Langstrom team didn't do quality analysis such as BLEU score and post-processing by combining a language model due to the time constraint. The final architecture is shown in the figure on the slide. Command to transforming speech wave file to English text is python recognize.py then path to the file. For example, try the following command: python recognize.py file, the path to the file .flag. The result will be as follows. We hope there would be a stew for dinner's turnips and carrots, for brushed potatoes and fat mutton pieces to be laid out in the thick, peppered flat fattened sauce. Actual value is he hoped there would be stew for dinner, turnips and carrots, and roast potatoes and fat mutton pieces to be laid out in thick peppered flour fattened sauce. This project, Speech-to-Text Wavenet, shows that wavenets are able to generate speech which mimics any human voice, which sounds more natural than the best existing text-to-speech systems, reducing the gap with human performance by over 50%. The above animation shows how a wavenet is structured with a fully convolutional neural network where the convolutional layers have various dilation factors that allow its receptive field to grow exponentially with the depth and cover thousands of time steps. At training time, the input sequence are really waveforms recorded from human speakers. At training, we can sample the network to generate synthetic utterances. At each step during sampling, a value is drawn from the probability distribution computed by the network. This value is then fed into the input and a new prediction from the next step is made. Building up samples one step at a time like this is computationally expensive, but we have found it essential for generating complex, realistic sounding audio. The following figure shows the quality of wavenets in a step from 1 to 5 compared with Google's current best TTS systems, parametric and concatenative, and with human speech using mean opinion scores MOS. MOS are a standard measure for subjective quality tests and were obtained in blind tests with human subjects from over 500 ratings on 100 test sentences. As we can see, wavenets reduce the gap between the state of the art and human level performance by over 50% for both US English and Mandarin Chinese. The Google parametric voice URL is https://storage.googleapis.com/deepminds-media/pixie/parametric-.wave. Wavenet voice is https://storage.googleapis.com/deepmind-media/pixie/us-english/wavenet-1.wave. The repository URL is https://github.com/beauty-suri/speech-to-text-wavenet. I'll be providing the URLs of the above mentioned resources in the description below. Fast Wavenet. Fast Wavenet is another project which implements to speed up the wavenet generation by eliminating redundant convolution operations. A Navy implementation of wavenet generation is order of 2 to the power of L, while fast wavenet is order of L, where L is the number of layers. While other wavenet repos focus on training on a large corpus of data and generating samples, ours mostly describe an efficient generation algorithm which is super simple and provides an example implementation. While this algorithm works well for autoregressive models like wavenet, it would be useful anytime you need to run a casual dilated convolutional neural network fast. For instance, classification or regression on streaming data. This fast wavenet generation algorithm paper, the URL is given in the below description, presents an efficient implementation of the wavenet generation process called fast wavenet. Compared to Navy implementation that has complexity order of 2 to the power of L. L denotes the number of layers in the network. Our proposed approach removes the redundant convolution operations by caching previous calculations, thereby reducing the complexity to the order of L time. Timing experiments show significant advantages of our fast implementation over a naive one. While this method is presented for wavenet, the same scheme can be applied anytime one wants to perform autoregressive generation or online prediction using a model with dilated convolution layers. The code for the fast wavenet generation algorithm method is publicly available. The key inside our fast wavenet algorithm is the following. Given a specific set of nodes in the graph, user will have sufficient information to compute the current output. User call these nodes the recurrent states in reference to recurrent neural networks, RNNs. Graves, 2013. An efficient algorithm can be implemented by caching these recurrent states instead of recomputing them from scratch every time a new sample is generated. Fast wavenet team generated from a model with 2 blocks of L layers each, using a Navy implementation and the fast wavenet algorithm implementation. Results are averaged over 100 repeats. When L is small, the Navy implementation performs better than expected due to the GPU parallelization of convolution operations. But when N is large, the efficient implementation really shines. Project 7 Horoward is a distributed training framework for TensorFlow, Keras, PyTorch, and MXNet, an open source component of Michelangelo's deep learning toolkit developed by Uber, which makes it easier to start and speed up distributed deep learning projects with TensorFlow. Uber found themselves in need of a way to train using a lot of data while maintaining short training times. To achieve this, Uber deep learning team turned to distributed training, and the details is found in their paper titled Horoward Fast and Easy Distributed Deep Learning in TensorFlow, or visit GitHub repository of Horoward, that is https://github.com/horoward/horoward and https://arxiv.org/abs/1802.05799. I'm providing the URLs in the description below also. The detailed explanation of this Horoward framework is given in the blog https://eng.uber.com/Horoward. I'm giving the URL in the description below also. Horoward, an open source library that improves on both abstractions to scaling. It employs efficient inter-GPU communication via ring reduction and requires only a few lines of modification to user code, enabling faster, easier distributed training in TensorFlow. Horoward can also distribute Keras programs by following the same steps. Horoward core principles are based on MPI concepts such as size, rank, and local rank, all reduce, all gather, and broadcast. Say, user launched a training script on 4 servers, each having 4 GPUs. If user launched 1 copy of the script per GPU, number 1, the size would be the number of processors. In this case, it is 16. Number 2, the rank would be the unique process ID from 0 to 15, that is size minus 1. Number 3, local rank would be the unique process ID within the server from 0 to 3. So these were the core principles on which Horoward was implemented. And Horoward team says the realization that a ring-all-reduce approach can improve both usability and performance motivated us to work on our implementation to address Uber's TensorFlow needs. Uber deep learning team adopted Baidu's draft implementation of the TensorFlow ring-all-reduce algorithm and built upon it. Uber deep learning team outlines their process as follows. Point number 1. They converted the code into standalone Python package called Horoward, named after a traditional Russian folk dance in which performers dance with linked arms in a circle, much like how distributed TensorFlow processors use Horoward to communicate with each other. At any point in time, various teams at Uber may be using different releases of TensorFlow. They wanted all teams to be available to leverage the ring all reduce algorithm without needing to upgrade to the latest version of TensorFlow, apply patches to their versions, or even spend time building out the framework. Having a standalone package allowed them to cut the time required to install Harvard from about an hour to a few minutes, depending on the hardware. Point number 2. Uber Deep Learning team replaced the Baidu Ring All Reduce implementation with NCCL. NCCL is NVIDIA's library for collective communication that provides a highly optimized version of Ring All Reduce. NCCL2 introduced the ability to run Ring All Reduce across multiple machines, enabling them to take advantage of its many performance-boosting optimization. Uber Deep Learning team added support for models that fit inside a single server, potentially on multiple GPUs, whereas the original version only supported models that fit on a single GPU. Point number 4. Finally, Uber Deep Learning team made several API improvements inspired by feedback they received from a number of initial users. In particular, they implemented a broadcast operation that enforces consistent initialization of the model on all workers. The new API allowed them to cut down the number of operations a user had to introduce to their single GPU program before. Now let's talk about how Uber team did visualization for this project. Harvard team wanted to do an easy debugging and profiling, so they developed a tool called Timeline. Harvard Timeline, a Harvard-focused profiling tool compatible with Chrome's About Tracing Trace Event Profiling Viewer. Users can use Harvard timelines to view exactly what each node was doing at each time step throughout a training job. This helps identify bugs and debug performance issues. Users can enable timelines by setting a single environment variable and can view the profiling results in the browser through Chrome:/tracing. Tensor Fusion, an algorithm that fuses tensors together before Uber Deep Learning team called Harvard's Ring All Reduce. As Uber Deep Learning team experimented with this approach, that is Tensor Fusion, they observed up to 65% improvement in performance on models with a large number of layers running on an unoptimized transmission control protocol (TCP) network. Uber Deep Learning team outlined how to use Tensor Fusion below. Point number 1. Determine which tensors are ready to be reduced. Select the first few tensors that fit in the buffer and have the same data type. Point number 2. Allocate a fusion buffer if it was not previously allocated. Default fusion buffer size is 64 MB. Point number 3. Copy data of selected tensors into fusion buffer. Point number 4. Execute the all reduce operation on the fusion buffer. Point number 5. Copy data from the fusion buffer into the output tensors. Point number 6. Repeat until there are no more tensors to reduce in the cycle. With Harvard, Tensor Fusion and other features built on top of Michelangelo, Uber Deep Learning team can increase the efficiency, speed and ease of use across their machine learning systems. Project number 8. Deep Voice Conversion. Deep Voice Conversion project deals with voice conversion on non-parallel data. It's deep neural networks implementation for voice conversion or voice style transfer using APIs of TensorFlow. This is a many-to-one voice conversion system. The main significance of this work is that user could generate target speakers utterances without parallel data like source waves, target waves, wave, text or wave, font, but only waveforms of the target speaker. All user need in this project is number of waveforms of the target speaker's utterances and only a small set of wave, font waves from a number of anonymous speakers. The model architecture consists of two modules: Net1 Phenomenon Classifier, Net2 Speech Synthesizer. So in the diagram you can see anonymous A's waveforms are fed in to Net1, which does the speech recognition and gives it as an input to the Net2, the speech synthesizer, which does the speech synthesis and gives the output in the B waveforms. Net1 Phenomenon Classification classifies someone's utterances to one of phenomena classes at every time step. Phenomena are speaker independent while waveforms are speaker dependent. Net2 is speech synthesizer. Synthesizes speeches of the target speaker from the phones. Deep voice conversion team applied CBHG, 1D convolution bank plus highway network plus bidirectional GRU modules that are mentioned in Tactron. CBHG is known to be good for capturing features from sequential data. Net1 is a classifier and Net2 is a synthesizer. The URL for deep voice conversion is github.com/endabi/deepvoice-conversion. Examples of soundbites are available on SoundCloud and the URL is https://soundcloud.com/endabi/set/voice-style-transfer-to-kate-winslet- with deep-neural-networks. Both the URLs are given in the description below. Coming to the ninth project, Neural Style Translation. The neural style algorithm synthesizes a pastiche by separating and combining the content of one image with the style of another image using convolution neural networks. In the slide, images are an example of transferring the artistic style of the Starry Night onto a photograph of an African lion. The Neural Style Translation Library is a TensorFlow implementation of neural style. Here in this project, transferring the style of various artworks to the same content image produces qualitative convincing results. Neural Style Translation is based on two projects, namely Torch of Lua implementation of neural style by J.C. Johnson, Torch Lua implementation of artistic videos by Manuel Ruder. Some of the prominent style features translation that can be done using this library are as follows. Number 1, content or style trade-off, that is, the relative weight of the style and content can be controlled. Number 2, multiple style images, that is, more than one style image can be used to blend multiple artistic styles. Number 3, style interpolation, that is, when using multiple style images, the degree of blending between the images can be controlled. Number 4, transfer style but not color. That means the color scheme of the original image can be preserved by including the flag -original_colors in the translation command. Number 5, textures. The algorithm is not constrained to artistic painting styles only. It can also be applied to photographic textures to create pareidolik images. Number 6, segmentation. That means style can be transferred to semantic segmentations in the content image. Multiple styles can be transferred to the foreground and background of the content image. Number 7, video translation. That means animations can be rendered by applying the algorithm to each source frame. For the best results, the gradient descent is initialized with the previous styled frame warped to the current frame according to the optical flow between the pair of frames. Loss functions of temporal consistence are used to penalize pixels excluding the disocculted regions and motion boundaries. Point number 8, gradient descent initialization. The initialization of gradient descent is controlled using the flag -init_image_type for single images and -init_frame_type or -first_frame_type for video frames. White noise allows an arbitrary number of distinct images to be generated, whereas initializing with a fixed image always converges to the same output. Point number 9, layer representation. The feature complexities and receptive field sizes increase down the CNN hierarchy. For full details, refer the report documentation at https://github.com/cysmith/neuralstyle-tf. The URL is given in the description below. Now moving to the last of the projects implemented using TensorFlow. That is Generative handwriting. Generative handwriting project uses long short-term memory mixture density network with the TensorFlow to generate cursive handwriting. The project was to implement to drive the point that long short-term memory recurrent neural networks can be used to generate complex sequence with long-range structure simply by predicting one data at a time. The approach is demonstrated for text where the data are discrete and online handwriting where the data are real valued. It is then extended to handwriting synthesis by allowing the network to condition its prediction on a text sequence. The resulting system is able to generate highly realistic cursive handwriting in a wide variety of styles. Alex Graves' paper shows that we can generate complex sequence using LSTM recurrent neural networks by combining mixed density network, a variant of neural network which can monitor the training progress of the mixed density network using TensorBoard. An interesting application of these networks is that it can be used to gain a better insight into the internal representation of the data. It would also be interesting to develop a mechanism to automatically extract high-level annotations from sequence data. In the case of handwriting, this could allow for more nuanced annotations than just text. For example, stylistic features, different forms of the same letter, information and stroke order, and so on. Coming to the next slide, TensorFlow Addons. TensorFlow Addons is a repository of contributions that conform to well-established API patterns, but implement new functionality not available in core TensorFlow. So in the sense, TensorFlow add-ons are basically Python package leveraging low-level API of core TensorFlow framework to implement solutions for special cases and enabling users utilize these specific composite solutions for their specific needs, thus helping the developers by allowing them to focus on the required functionality instead of worrying setup and initialization of the applications. TensorFlow Addons is maintained by SIG Addons team. Some of the popular TensorFlow add-ons are 1. TensorFlow Probability, also known as TensorFlow P, is a Python library built on TensorFlow that makes it easy to combine probabilistic models and deep learning on modern hardware, that is TPU, GPU, etc. It's for data scientists, statisticians, machine learning researchers, and practitioners who want to encode domain knowledge to understand data and make predictions. TensorFlow Probability provides integration of probabilistic methods with deep networks, gradient-based inferences using automatic differentiation, and scalability to large data sets and models with hardware acceleration, that is GPUs, and distributed computations. TensorFlow includes functionalities like number 1, a wide selection of probability distributions and bijectors. Number 2, tools to build deep probabilistic models including probabilistic layers and the Edward 2 language. Number 3, variational inferences and Markov chain Monte Carlo. Number 3, optimizers such as Nelder-Mead, BFGS, and SGLD. Since TensorFlow Probability inherits the benefits of TensorFlow, you can build, fit, and deploy a model using single language throughout the life cycle of model exploration and production. The GitHub repository URL is https://github.com/tensorflow/probability. I'll be giving the URL in the description below. Number 2 add-on is Tensor to Tensor, or T2T for short, is a library of deep learning models and data sets designed to make deep learning more accessible and accelerate machine learning research. Tensor to Tensor T2T is an open source system for training deep learning models in TensorFlow. T2T facilitates the creation of state-of-the-art models for a wide variety of machine learning applications such as translation, parsing, image caption, and more. T2T facilitates enabling the exploration of various ideas much faster than previously possible. TensorFlow 2.0 release also includes a library of datasets and models, including the best models from a few recent papers. That is, attention is all you need, depth-wise separable convolutions for neural machine translation, and one model to learn them all. These were the recent papers to help kickstart your own deep learning research. T2T is actively used and maintained by researchers and engineers within the Google Brain team and a community of users. For more details, visit https://ai.googleblock.com/2017/06/accelerating deep learning research-research.html, and the GitHub repository URL is https://github.com/tensorflow/tensor2tensor. The URLs are given below in the description. The add-on number 3 is TensorFlow Agents. TensorFlow Agents is a library for reinforcement learning in TensorFlow. In TensorFlow Agents, the core elements of reinforcement learning algorithms are implemented as agents. An agent encompasses two main responsibilities: defining a policy to interact with the environment, how to learn or train that policy from collected experience. Currently, the following algorithms are available under TensorFlow Agents. 1. DQN, the human level control through deep reinforcement learning, by Min et al. 2015. Double DQN, deep reinforcement learning with double Q learn, by Hassett et al. 2015. Double DPG, continuous control with deep reinforcement learning, Lillicrap et al. 2015. TD3, addressing function approximation error in actor-critic methods, by Fujimoto et al. 2018. Reinforce simple statistical gradient following algorithms for connectionist reinforcement learning, by Williams in 1992. PPO, proximal policy optimization algorithms, by Schluman et al. In 2017. SAC, soft actor critic, by Harnauja et al. In 2018. The GitHub repository for TensorFlow Agents is https://github.com/tensorflow/agents. I'll be providing the URL in the description below. The fourth TensorFlow add-on is TensorFlow Federated, also known as TensorFlow F, is an open source framework for machine learning and other computations on decentralized data. TensorFlow F has been developed to facilitate open research experimentation with federated learning, an approach to machine learning where a shared global model is trained across many participating clients that keep their training data locally. For example, FL has been used to train prediction models for mobile keywords without uploading sensitive typing data to servers. TensorFlow F enables developers to simulate the included federated learning algorithms on their models and data, as well as to experiment with novel algorithms. The building blocks provided by TensorFlow F can also be used to implement non-learning computation such as aggregated analytics or decentralized data. TensorFlow's F interfaces are organized in two layers. Federated Learning FL API. This layer offers a set of high-level interfaces that allow developers to apply the included implementation of federated training and evaluation to their existing TensorFlow models. Federated Learning FL API. This layer offers a set of high-level interfaces that allow developers to apply the included implementation of federated training and evaluation to their existing TensorFlow models. Federated Core FC API. At the core of the system is a set of lower-level interfaces for concisely expressing normal federated algorithms by combining TensorFlow with distributed communication operators within a strongly typed function programming environment. This layer also serves as the foundation upon which we have built federated learning. TensorFlow F enables developers to declaratively express federated computations so they could be deployed to diverse runtime environments. Included with TensorFlow F is a single machine simulation runtime for experiments. Now, the TensorFlow add-on number 5, that is TensorFlow Privacy, is a library for training machine learning models with privacy for training data. TensorFlow Privacy, a Python library that includes implementation of TensorFlow optimizers for training machine learning models with differential privacy. The library comes with tutorials and analysis tools for computing the privacy guarantees provided. The repository URL is https://github.com/tensorflow/privacy. I'll be providing the URL in the YouTube description. TensorFlow add-on number 6, Mesh TensorFlow (MTF), is a language for distributed deep learning capable of specifying a broad class of distributed TensorFlow computations. The purpose of Mesh TensorFlow is to formalize and implement distribution strategies for your computations, graph over your hardware or processors. For example, split the batch over rows of processors and split the units in the hidden layer across columns of processors. Mesh TensorFlow is implemented as a layer over TensorFlow. The Mesh TensorFlow approach to distributed computation is as follows. Number 1. A mesh is an n-dimensional array of processors connected by a network. Number 2. Each tensor is distributed, that is split and or replicated across all processors in a mesh. Number 3. Tensor dimensions and mesh dimensions are named. The layouts of all tensors follow from a set of user-defined layout rules which specify which tensor dimensions are split across which mesh dimensions. This ensures that corresponding dimensions in different tensors are split in the same manner. Point number 4. Layouts do not affect results, only performance. Point number 5. The implementation of an operation involves parallel computation on all processors in the mesh and sometimes also collective communication. A processor usually just manipulates the slices of an input tensors already resident on that processor and produces the slice of the output that goes on that processor. GitHub repository URL is https://github.com/tensorflow/mesh. Tensor add-on number 7 is Dopamine. Dopamine is a research framework for fast prototyping of reinforcement learning algorithms. It aims to fill the need for a small, easy grouped code base in which users can freely experiment with wild ideas, that is speculative research. Dopamine design principles are easy experimentation, that is make it easy for new users to run benchmark experiments. Second point, flexible development, that is make it easy for new users to try out research ideas. Point number 3, compact and reliable, that is provide implementation for a few battle tested algorithms. Point number 4, reproducible, that is facilitate reproducibility in results. In particular, our step follows the recommendations given by Mercado et al. Specifically, our rainbow agent implements the 3 components identified as most important by Hessel et al. That is, n-step Bellman updates, prioritized experience reply, distributed reinforcement learning. Finally, it also provides an implementation of DQN. So the Dopamine repository URL is https://github.com/google/dopamine. You can visit this repository for more details on dopamine, and the URL is presented in the description below. The Tensor add-on number 8 is TRFL, also known as Truffle. It represents a collection of key algorithmic components that we have used internally for a large number of our most successful agents such as DQN, DDPG, and the importance of weighted actor learner architecture. A typical deep reinforcement learning agent consists of a large number of interacting components. At the very least, these include the environment and some deep network representing values or policies, but they often also include components such as learned model of the environment, pseudo reward functions, or a replay system. The TRFL library includes functions to implement both classical RL algorithms as well as more cutting-edge techniques. The loss functions and other operations provided here are implemented in pure TensorFlow. Since this library is used extensively within DeepMind, DeepMind will continue to maintain it as well as add new functionalities over time. Truffle library was created by research engineering team at DeepMind. Tensor add-on number 9 is Ragged Tensors. Now moving to the number 9 TensorFlow add-on is Ragged Tensors. Ragged Tensors are the TensorFlow equivalent of nested variable length lists. They make it easy to store and process data with non-uniform shapes, including number 1 variable length features such as set of actors in a movie. Number 2 batches of variable length sequential inputs such as sentences or video clips. Number 3 hierarchical inputs such as text documents that are subdivided into sections, paragraphs, sentences, and words. Point number 4 individual fields in structured inputs such as protocol buffers. Ragged tensors are supported by more than 100 TensorFlow operations, including math operations such as tf.add and tf.reduce_mean, array operations such as tf.concat and tf.tile, string manipulation operations such as tf.substring, and many others. There are also a number of methods and operations that are specific to ragged tensors, including factory methods, conversion methods, and value mapping operations. For a list of supported operations, see the tf.ragged package documentation available on tensorflow.org. Ragged tensor shape restrictions are as follows. The shape of a ragged tensor is currently restricted to have the following form. Number 1, a single uniform dimension. Number 2, followed by one or more ragged dimensions. Number 3, followed by 0 or more uniform dimensions. The GitHub repository URL is https://github.com/docs/master/site/en/guide/ragged_tensor.ipnyb. The URL will be provided in the description below. Tensor add-on number 10 is Unicode operations or Unicode OPS. In TensorFlow, Unicode strings are UTF-8 encoded by default. Unicode strings are handled differently in TensorFlow for various scientific reasons. They are represented and manipulated using TensorFlow's Unicode-specific operations, which are analogous to standard string operations. These operations can be found in the tf.string data type. A tf.string tensor would hold byte strings of varying lengths because the byte string are treated as atomic units. The string length is not included in the tensor dimension. So there are two standard ways to represent a Unicode string in TensorFlow. Number 1, string scalar, where the sequence of code points is encoded using a known character encoding. Number 2, int32 vector, where each position contains a single code point. TensorFlow provides operations to convert between these different representations. tf.strings.encode_decode is an operation which converts an encoded string scalar to a vector of code points. tf.strings.unicode_encode is an operation which converts a vector of code points to an encoded string scalar. tf.string.encode_transcode is an operation which converts an encoded string scalar to a different encoding. The GitHub URL is https://github.com/tensorflow/docs/blog/master/site/unicode.ipynb. The URL will be given in the description below. Tensor add-on 11 is TensorFlow Ranking. TensorFlow Ranking is a library for learning to rank LTR techniques on the TensorFlow platform. It contains the following components. Number 1, commonly used loss functions including pointwise, pairwise and lightwise losses. Point number 2, commonly used ranking metrics like mean reciprocal rank MRR and normalized discounted cumulative gain NDCG. Point number 3, multi-item also known as group-wise scoring functions. Point number 4, lambda loss implementation for direct ranking metric optimization. Point number 5, unbiased learning to rank from biased feedback data. Google envisioned that this library will provide a convenient open platform for hosting and advancing the state-of-the-art ranking models based on deep learning techniques, and thus facilitated both academic research as well as the industrial application. The GitHub repository URL is https://github.com/tensorflow/ranking. I'll be providing the URL in the description below also. TensorFlow add-on number 12 is Magenta. Magenta is an open source research project exploring the role of machine learning as a tool in the creative process. Magenta is distributed as an open source Python library powered by TensorFlow. This library includes utilities for manipulating source data, that is primarily music and images, using this data to train machine learning models and finally generating new content from these models. Some of the featured projects of this library are Magenta Studio, which is a collection of music plugins built on Magenta's open source tools and models. Onset and Frames, which is transcribing piano with a neural network. Music VAE, which is creating palettes for blending and exploring musical loops and scores. NSynth, which is making music using new sounds generated with machine learning. The GitHub repository for Magenta is as follows: https://github.com/tensorflow/magenta. I'll be providing the URL in the description below. TensorFlow add-on number 13 is Nucleus. Nucleus is a library of Python and C++ code designed to make it easy to read, easy to write and analyze data in common genomics file formats like SAM and VCF. In addition, Nucleus enables painless integration with TensorFlow machine learning framework. As anywhere a genomics file is consumed or produced, a TensorFlow TF records file may be used instead. The GitHub repository for this library is https://github.com/google/nucleus. Moving to the next slide, that is TensorFlow tools. We'll explore the tools to support and accelerate TensorFlow workflows. Number 1 is Colab. Colaboratory is a free Jupyter notebook environment that requires no setup and runs entirely in the Google Cloud, allowing you to execute TensorFlow code in your browser with a single click. Tool number 2 is TensorBoard, a suite of visualization tools to understand, debug and optimize TensorFlow programs. Tool number 3, What If tool, is a tool for code-free probing of machine learning models, useful for model understanding, debugging and fairness. Available in TensorBoard and in Jupyter or in Colab notebooks. Tool number 4 is MLPref, that is Machine Learning Performance, is a broad machine learning benchmark suite for measuring performance of machine learning software frameworks, machine learning hardware accelerators and machine learning cloud platforms. Tool number 5 is XLA. XLA or Accelerated Linear Algebra is a domain-specific compiler for linear algebra that optimizes TensorFlow computations. The results are improvements in speed, memory usage, and probability on sensor and mobile platforms. TensorFlow Playground. It's a tool for tinkering with the neural network in your browser. Don't worry, you can't break it. So it is basically a kind of testing the neural network, typically from a simple browser. Tool number 7 is TensorFlow Research Cloud. TensorFlow Research Cloud or TensorFlow RC program enables researchers to apply for access to a cluster of more than 1,000 cloud TPUs at no charge to help them accelerate the next wave of research breakthroughs. We have seen the complete overview of ecosystem of TensorFlow now and how it has been used by various scientists and engineers and technocrats. So let's try to know how we can use it locally or remotely, or we can try it first on Google Cloud. So let's understand how to install TensorFlow. TensorFlow installation. There are two ways of installation. One is to install the current release only for CPU, and the other is to use the GPU package for CUDA enabled GPU cards. The first command will install TensorFlow for local system with only CPU access, that is pip install TensorFlow, and the second command will install locally with both CPU and graphics card access, that is pip install TensorFlow-GPU. Both the commands has to be executed on terminal windows. If you don't want to install and want to just try it, then you can go to Colab website, that is https://colab.research.google.com/notebooks/welcome.ipynb. I'll be providing this URL in the description below. This website will open a demo notebook to try TensorFlow code and tutorials, so you can learn deep learning techniques without installing TensorFlow. To run a TensorFlow inside a container like Docker, Google provides TensorFlow Docker images. In the slide, the TensorFlow Docker images are already configured to run TensorFlow. A Docker container runs in a virtual environment and is the easiest way to set up GPU support. So the commands that you have to use is docker pull TensorFlow/TensorFlow to download the latest image, and docker run -it-p 8888:8888 space TensorFlow/TensorFlow to start the Jupyter Notebook server. Please make sure that you have Docker installed on your system before running these commands. This will help you to have your virtual environment running for TensorFlow trainings. Coming to the last one is the Google Colab, an easy way to learn and use TensorFlow. No install is necessary, just run the TensorFlow tutorials directly in the browser with Colaboratory, a Google research project created to help disseminate machine learning education and research. It's a Jupyter Notebook environment that requires no setup to use and runs entirely on the cloud. For more details, visit Google's website, which I have already given the URL down below. So in this way you can see the image of a Google Colab demo notebook for trial runs and learning purpose. Now let's understand in detail what is TensorFlow and its components. So we are now moving to the programming or coding aspect of TensorFlow. Tensors is defined as a multi-dimensional array containing data from datasets. For example, 1D tensor is vector, 2D tensor is a matrix, 3D tensor is a cube. Similarly, we can assume that 4D tensor as a vector of cubes, 5D tensor is a matrix of cubes, 6D tensor as a cube of cubes, etc. So mathematically, what's a tensor? Formally, tensors are multilinear maps from vector spaces to the real numbers. That is, a function f maps vector v of p copies by q copies to real set R. So a scalar is a tensor. That means a tuple with elements f function such that R implies R, comma, f of E1 is equal to C. A vector is a tensor, is a tuple defined as f colon R raised to n implies R, comma, f of EI is equal to VI. A matrix is a tensor defined by a tuple whose elements are f colon R raised to n multiplied by r raised to n implies r, comma, f of ei, comma, ej is equal to aij. So a tensor can be represented as a multidimensional array of numbers. TensorFlow tensors has some unique following properties. Rank defines how many dimensions the tensor contains. Shape, which defines the size of each dimension of the data. D-type, which defines the data type of the tensor. Now let's understand in detail what is TensorFlow and its components. Tensors is defined as a multi-dimensional array containing data from datasets. For example, 1D tensor is a vector, 2D tensor is a matrix, 3D tensor is a cube. Similarly, we can assume that 4D tensor as a vector of cubes, 5D tensor is a matrix of cubes, 6D tensor as a cube of cubes, etc. So mathematically, what's a tensor? Formally, tensors are multilinear maps from vector spaces to real numbers. That is, function f maps vector v of p copies by q copies to real set R. So a scalar is a tensor defined by a tuple whose element f is such that R implies R, comma, function f of ei is equal to c. Close the tuple. A vector is a tensor which is defined by a tuple whose element is f colon r raised to n implies r, comma, f of ei is equal to vi. Close the tuple. A matrix is a tensor which is defined by a tuple whose element f is such that r raised to n multiplied by r raised to m implies r, comma, function f of ei, comma, ej is equal to aij. Close the tuple. So it is common to have fixed biases. A tensor can be represented as a multidimensional array of numbers. TensorFlow tensors have some unique following properties. Number 1, rank defines how many dimensions the tensor contains. Number 2, shape, which defines the size of each dimension of the data. Number 3, D-type, which defines the data type of the tensor. Now let me explain what is tensor rank. The rank of a tensor is not the same as the rank of the matrix. Rank of a tensor is the number of indices which require to uniquely select each element of the tensor. Rank is also known as order, degree, or endims. As the following table shows, each rank in TensorFlow corresponds to a different mathematical entity. Rank 0 mathematical entity is scalar. Rank 1 vector. Rank 2 is a matrix. Rank 3 is a 3 tensor or a cube of numbers. Rank n is an n tensor. You get the idea.
Now let me explain about tensor shape. The shape of a tensor is the number of elements in each dimension. TensorFlow automatically infers shapes during graph construction. These inferred shape might have known or unknown rank. If the rank is known, the size of each dimension might be known or unknown. Shape can be represented via Python list or tuples of hints or with the tf.tensor shape. Now let me explain about tensor operations. An operation takes 0 or more tensors, performs some computation, and produces 0 or more tensors. Each operation can be handed a constant, array, matrix, or n-dimension matrix. Another word for n-dimension matrix is a tensor. A 2-dimensional tensor is equivalent to a m by m matrix, as you can see in the slide. TensorFlow contains all the basic operations. You can begin with a simple one. You will use TensorFlow method to compute the square of a number. This operation is a straightforward because only one argument is required to construct the tensor. As shown in the top left side of the slide, the square of a number is constructed with tf.square root of x with x as a floating number. X is equal to tf.constant of 2.0, comma d type is equal to tf.float 32. Print of tf.square root of x. Output. The output is tensors within round braces, within double quotes, square root colon 0, close the quotes, comma, shape equal to 1 comma, close the round bracket, comma, d type is equal to float 32, close the round bracket. Following is a list of commonly used operations. Each operation requires one or more arguments. tf.add within round brackets a comma b, tf.subtract within round bracket a comma b, tf.multiply within round bracket a comma b, tf.div within round bracket a comma b, tf.pow within round bracket a comma b, tf.exp within round bracket a, tf.square root within round bracket a. The TensorFlow data types and primitives. TensorFlow has its own data types. We'll discuss data types in TensorFlow and how to use variables from this slide onwards. TensorFlow accepts Python native types like booleans, strings, and numeric, that is int and float, but you should use TensorFlow data types instead. Following is the list of TensorFlow data types. dt_float is similar to or analogous to Python type tf.float32, that is 32 bits of floating point. dt_double is analogous to tf.float64, that is 64 bits floating point. dt_int8, tf.int8, that is 8 bits of signed integer. dt_int16, tf.int16, that is 16 bytes of signed integer. dt_32, that is tf.int32, that is 32 bits of signed integer. dt_int64, tf.int64, that is 64 bits signed integer. dt_u_int8, that is tf.u_int8, that is 8 bits of unsigned integer. dt_string, that is tf.string, that is variable length byte arrays. Each element of a tensor is a byte array. dt_bool, that is tf.bool, that is boolean. dt_complex64 is tf.complex64, that is complex number made of 2 bytes, 232 bits floating points, real and imaginary parts. dt_complex128, that is tf.complex128, that is complex number made of 2 64 bits floating points, one for real and the one for imaginary parts. dt_q_int8, that is tf.q_int8, that is 8 bits of signed integer used in quantized operations. dt_q_int32 is in tf.quint32, that is 32 bits signed integer used in quantized operations. dt_q_int32 is tf.q_int32, that is 32 bits signed integer used in quantized operations. dt_q_int8, that is tf.q_int8, that is 8 bits of unsigned integer used in quantized operations. Also note that TensorFlow data types integrate seamlessly with NumPy. In TensorFlow, variables maintain state across execution of the graph. I'll be explaining about this in the next few slides. Now we'll be starting to code. So let's start the get started part of coding. In TensorFlow, we have to set up the data variables, placeholders, and model before we tell the program to train and change the variables to improve the predictions. TensorFlow accomplishes this through the computational graph. We tell it to minimize a loss function, and TensorFlow does this by modifying the variables in the tensor. TensorFlow knows how to modify the variables because it keeps track of the computation in the tensor and automatically computes the gradients for every variable. Because of this, we can see how easy it can be to make changes and try different data sources. So let's begin the programming part with the default part of it. That is, we start the TensorFlow code with this first statement, that is, import TensorFlow as TF. Also, you need to know that TensorFlow computation starts after eval method is invoked. TensorFlow requires explicit evaluation. Till then, the computation doesn't have any data or value inside the graph. So we start with the line number 1, where a is equal to numpy np dot zeros within bracket 2, passing the tuple 2, 2. And in the next line of the statement, ta is equal to tf dot zeros with the parameter of a tuple 2, 2. Then we print a, which gives us a square within square bracket, another square bracket 0, 0, close the square bracket, opening square bracket 0, 0, and close the bracket. So this has a value of a double array. Now print ta, tensor. It prints tensor of double quote zeros underscore 1 colon 0 close the quote comma shape is equal to within round bracket 2, 2 comma d type is equal to float 32 close the round bracket. So we see that print ta prints a tensor but no values. Print ta dot eval will give you the same output as we got it in the print a statement, that is opening square bracket 0 dot 0 dot close the right bracket, open the left square bracket 0 dot 0 dot close the right bracket, close the right bracket. So this output was similar to print a. The TensorFlow computes using a computation graph which needs to be evaluated to get a value. Hence we call eval method on the tensor a. To understand the TensorFlow programming learning curve in a simplified or in a one sentence, then you need to be aware of 3 simple modules of TensorFlow framework, namely: number 1, TensorFlow Learn, that is tf.contrib.learn, is a simplified interface that helps users transition from the world of one-liner such as scikit-learn. Number 2, TensorFlow Slim, that is tf.contrib.slim, is a lightweight library for defining, training and evaluating complex models in TensorFlow. Point number 3, high-level API, namely Keras, which is a high-level API to build, train deep learning models. Keras is used for fast prototyping, advanced research and production with 3 key advantages, namely point number 1 or advantage number 1 is user-friendly, that is Keras has simple, consistent interface optimized for common use case. It provides clear and actionable feedback for user errors. Advantage number 2. The advantage is modular and composable. That is, Keras models are made by connecting configurable building blocks together with few restrictions. Advantage number 3. Easy to extend. Write custom building blocks to express new ideas for research, create new layers, loss functions, and develop state-of-the-art models. TensorFlow Slim. URL is https://github.com/TensorFlow/tree/master/TensorFlow/contrib/slim. TensorFlow-Slim is a lightweight library for defining, training, and evaluating complex models in a TensorFlow. Components of tf.slim can be freely mixed with native TensorFlow, as well as other frameworks such as tf.contrib.learn. So now let's explore how to use TensorFlow Slim. You can use TensorFlow Slim in the code by calling the import statement import TensorFlow.contrib.slim as Slim. Then we can use all its classes and related functions. Why TensorFlow Slim? TensorFlow Slim is a library that makes defining, training and evaluating neural networks simple. That is, allow the user to define models much more compactly by eliminating boilerplate. This is accomplished through the use of argument scoping and numerous high-level layers and variables. These tools increase readability and maintainability, reduce the likelihood of an error from copy and pasting hyperparameter values, and simplifies hyperparameter tuning. TensorFlow makes developing models simple by providing commonly used regularizers. Several widely used computer vision models, example EGG, LXNet, have been developed in Slim and are available to users. These can either be used as black boxes or can be extended in various ways. Example, by adding multiple heads to different internal layers, Slim makes it easy to extend complex models and to start training algorithms by using pieces of pre-existing model checkpoints. What are the various components of TensorFlow Slim? Let's see the components of the TensorFlow Slim. It is composed of several parts which were designed to exist independently. Some of these include the following are the main pieces or packages of TensorFlow Slim. Number 1, Arc Scope. TensorFlow Slim's Arc Scope package provides a new scope named arc_scope that allows a user to define default arguments for specific operations within that scope. TensorFlow Slim's data package contains TensorFlow Slim's dataset definition, data providers, parallel dealer, and decoding utilities. Next comes evaluation. The TensorFlow Slim evaluation package contains routines for evaluating models. Next is layers. TensorFlow Slim's layer module contains high-level layers for building models using TensorFlow. Learning. TensorFlow Slim's learning module contains routines to training models. Losses. TensorFlow Slim's losses package contains commonly used loss functions. Metrics. TensorFlow Slim metrics package contains popular evaluation metrics. Nets. TensorFlow Slim's nets package contains a popular network definition such as EGG and LXNet models. Queues. TensorFlow Slim's queue package provides context manager for easily and safely starting and closing queue runners. Regularizers. TensorFlow Slim's regularize package contains weight regularizers. Variables. TensorFlow Slim's variables namespace provides convenience wrappers for variable creation and manipulation. Another important module of TensorFlow which I haven't mentioned here is TensorFlow Learn. As of now, the TensorFlow version 2.0 onwards, it has been deprecated. So if you want to use TensorFlow version 1.0, you can learn about it by visiting the website tflearn.org. TensorFlow Learn is a deep learning library featuring a high-level API for TensorFlow. TensorFlow Learn is a modular and transparent deep learning library built on top of TensorFlow. It was designed to provide higher-level API to TensorFlow in order to facilitate and speed up experimentation while remaining fully transparent and compatible with it. TensorFlow Learn features include: number 1, easy to use, understand, high-level API for implementing deep neural networks with tutorial and example. Number 2, fast prototyping to highly modular built-in neural network layers, regularizers, optimizers, metrics. Fully transparency over TensorFlow. All functions are built over tensors, can be used independently over TensorFlow Learn. Powerful helpful function to train any TensorFlow graph with support on multiple inputs, outputs, and optimizers. Easy and beautiful graph visualization with details about weights, gradients, and activations and more. Effortless device placement for using multiple CPU or GPU. The high-level API currently supports most of the recent deep learning models such as convolutions, LSTM, BI, RNN, batch norm, PRLU, residual networks, generative networks. In the future, TensorFlow Learn is also intended to stay updated with the latest deep learning techniques. Now let's move to the slide of graphs and sessions. Let's understand major concepts of TensorFlow programming. We'll start with the very core part of TensorFlow framework, that is, in TensorFlow, we have to set up the tensor, variables, placeholders, and model before we tell the program to train and change the variables to improve the predictions. TensorFlow accomplishes this through the component known as Computational Graph.
To understand the computational graph, we need to know what is session and what is graph. So let's start with session. A session is basically the backbone of TensorFlow program. TensorFlow uses tf.session class to represent a connection between client program, typically a Python program, although a similar interface is available in other languages and C++ runtime. A tf.session object provides access to devices in the local machine and remote devices using the distributed TensorFlow runtime. It also caches information about your tf.graph so that you can definitely run the same computation and multiple times. A session fires up the program to get the constants ready and perform the desired operation. It can be done in the following way. Like create a session and assign it a variable ses so we can pull it later. This is within the session. Evaluate the graph to fetch the value of A. So let's read the code. Import TensorFlow as tf. A is equal to tf.add of 3, 5. Ses is equal to tf.session. Print ses.run. Ses.close. Now retrieve the value of A. We do that by using session.run result function inside the print function. Lastly, we close the session by using ses.close function. So this TensorFlow session object is a session encapsulating the environment in which operation objects are executed and tensor objects are evaluated. In the first statement, A is equal to tf.constant of 5.0. A gets initialized with the constant value. B is equal to tf.constant of 6. C is equal to A into B. tf.session as ses. Print ses.run of C. C.eval is just a syntactic sugar for ses.run of C in the currently active session. So when we call print cf.eval, it does the same thing as session.run of C. It prints the value that is there inside the session object C. There is another type of session called as tf.interactive session. It's just a convenient syntactic sugar for keeping a default session open in IPython. Session.run of C is an example of TensorFlow fetch. Since tf.session owns physical resources such as GPUs and network connections, it is typically used as a context manager in a with block that automatically closes the session when you exit the with block. It is also possible to create a session without using with block, but you should explicitly call tf.session.close when you are finished with it to free the resources. X equal to 2, y is equal to 3, op1 is equal to tf.add x, y. op2 is equal to tf. Multiplication x, y. Operation 3 is equal to tf.power of op2, op1 with tf.session as ses. op3 is equal to ses.run op3. So you can see in the graph x, y tensors are fed into multiplication operations, and then it's fed into POW operations, which is then again further fed into add operations, and then you retrieve x and y value. The salient points of TensorFlow computation graph. TensorFlow computation defines a computation graph that has no numerical value until evaluated. TensorFlow programs are usually structured into construction phase that assembles a graph and an execution phase that uses a session to evaluate ops in the graph. As shown in the figure, 5 and 3 are input hyperparameters. They are fed into mu1 and add, which is further, after processing, it's fed into the add node, which further processes and sends the tensor which is having a value of 22. All computations add nodes to global default graphs. You can see more detailed information in the TensorFlow docs. In TensorFlow board, computations are represented as graphs, and nodes are the operations in those operations. Edges are the tensors, multi-dimensional arrays, as shown in the TensorBoard visualized figure. If you take the statement or the code import TensorFlow as TF. A is equal to tf.add 3,5. Over here the node is part of the TensorFlow default graph and A is the tensor. Y, X, Y, the TensorFlow automatically names nodes when you don't explicitly name them. So X is equal to 3, Y is equal to 5. In other words, we can say that a TF.graph contains two relevant kinds of information. One, graph structure, the nodes and edges of the graph indicating how individual operations are composed together, but not prescribing how they should be used. Graph structure is like assembly code. Inspecting it can convey some useful information, but it does not contain all of the useful context that source code conveys. Point number 2. Graph collections. TensorFlow provides a general mechanism for storing collections of metadata in a tf.graph. The tf.add_to_collection function enables you to associate a list of objects with a key, where tf.graph keys define some of the standard keys, and tf.get_collection enables you to look up all objects associated with the key. Many parts of the TensorFlow library use this facility. For example, when you create a tf.variable, it is added by default to collections representing global variables and trainable variables. When you later come to create a tf.train.saver or tf.train.optimizer, the variables in these collections are used as the default arguments. Most TensorFlow programs can start with the dataflow graph construction phase. In this phase, you invoke TensorFlow API functions that construct new tf.operations, that is, node as visible in TensorBoard, and tf.tensor, that is, edge as visible in the TensorBoard, and add them to a tf.graph instance. TensorFlow provides a default graph that is implicit argument to all API functions in the same context. Most programs rely solely on the default graph. For example, calling tf.constant of 42 creates a single tf.operation that produces the value 42, adds it to the default graph as you see in the default flow graph. Figure B has the value constant, that is, in our example, value 42, and returns a tf.tensor that represents the value of the constant. Calling tf.maxmal of x, y creates a single tf.operation that multiplies the values tf.tensor objects x and w, adds it to the default graph, and returns a tf.tensor that represents the result of the multiplication. Finally, you get a computational graph having all these operations added and ready to be executed when session.run or eval function is invoked. Now let's understand the basic programming elements of TensorFlow. TensorFlow constant. tf.constant is used for initializing immediately. It creates a constant tensor. The resulting tensor is populated with values of type d-type as specified by the arguments value and optionally shape. Constant 1D tensor populated with value list can be written as tensor equal to tf.constant within round bracket square bracket of 1, 2, 3, 4, 5, 6, 7, close the square bracket, close the round bracket, implies or gives a vector of 1, 2, 3, 4, 5, 6, 7. Similarly, the constant of 2D tensor populated with scalar value -1 code can be written as tensor is equal to tf.constant of -1.0, shape is equal to within square brackets 2, 3, close the square bracket, close the round braces, gives within square bracket -1, -1, close the square bracket, open another square bracket, -1, -1, close the square bracket and close the outer square bracket. Args for the tf.construct function is value. A constant value for list of output type d-type is passed. D-type, the type of the elements of the resulting tensor. Shape, optional dimensions of the resulting tensor. Name, optional name for the tensor. Verify_shape, the boolean that enables verification of shape of values. Final return value of that constructor function is the constant tensor. Now we move to the TensorFlow placeholder, another programming element of TensorFlow. tf.placeholder is a function which initialize value is not required. tf.placeholder, which is a function where initial value is not required, assign value via feed_date at runtime. tf placeholder function are not modified during training. A placeholder is simply a variable that we will assign data to at a later date. It allows us to create our operations and build our computation graph without needing the data. In TensorFlow terminology, we then feed data into the graph through these placeholders. Let's read the code. Import TensorFlow as tf. Variable a is equal to tf.placeholder within brackets within quotes float. b is equal to tf.placeholder within bracket within quotes float. c is equal to tf.multiply of a comma b. Feed_date is equal to within curly braces a colon 2 comma b colon 3 close the curly braces with tf.session as ses print of ses.run of c comma feed_d comma placeholders and feed dictionaries. Inputting data with tf.convert _2 tensors is convenient but doesn't scale. Use tf.placeholder variables, which are dummy nodes that provide entry points for data to computational graph. A feed_date is a Python dictionary mapping from tf.placeholder vars or their names to data, numpy, arrays, lists, etc. So let's read the code which explains placeholders and feed dictionaries. Input 1 is equal to tf.placeholder of tf.float32. Input 2 is equal to tf.placeholder of tf.float32. tf.placeholder is defined here for objects for data entry. Output is equal to tf.mul of input comma input 2 close the round bracket. With tf.session as ses print of ses.run open round bracket within square bracket output comma feed_date is equal to within curly braces input 1 colon square bracket 7 dot close the square bracket comma input 2 colon square bracket 2 close the square bracket close the curly braces close the round bracket close the round bracket. Coming out of the with block we get a output of array of 14 comma d type is equal to 432. So this print statement fetches the value of output from computation graph and the feed_date feeds the data into the computation graph. Now let's learn TensorFlow variables. tf.variable is a class with the following characteristics. That is, tf variable initialize value is required, tf variable updated during training, tf variable in-memory buffer is saved or restored from the disk, tf variable can be shared between works in distributed environment. In a trainer model, we use variables to hold and update parameters. Variables are in-memory buffers containing tensors. So this is a kind of definition for variables. All tensors we have used previously have been a constant tensors, not variables. TensorFlow variables must be initialized before they have values. So let's read the code related to TensorFlow variables. W1 is equal to tf.ones within round bracket pass a tuple 2, comma 2. W2 is equal to tf.variable within round braces we pass tf.zeros with parameter of a tuple 2, comma 2, comma name is equal to weights with tf.sessions as ses print of ses.run of w1 close the round bracket ses.run comma within round braces tf.initialize all underscore variables close the round braces print session.run of w2. Note that initialization step tf.initialize all variables, which this makes all the variables to be updated with values. In the statement w is equal to tf.variable tf.zeros of 2, 2 name weights r is equal to tf.variable within opening bracket tf.random_normal
with round bracket, tuple 2, 2 is passed with comma name is equal to random is. These two statements, variable objects can be initialized from constants as well as from random values. Now, how to fetch the variable state? Let's read the code which fetches the variable state. Input is equal to tf.constant of 3, 0. Input 2 is equal to tf.constant 2, 0. Input 3 is equal to tf.constant 5, 0. Interval is equal to tf.add of input 2, input 3. Annual is equal to tf.annual open round bracket input 1, intermed close the round bracket. With tf.session as says, result is equal to ses.run within round bracket within square bracket annual, intermed close the square bracket close the round bracket print result. So you get the output as 21, 7.0. Calling ses.run inside the if block with a variable parameter on tf.session object retrieves its value. Can retrieve multiple variables simultaneously with ses.run, like it can be a vector also. See fetches in TensorFlow docs. Now we will move to the most interesting part of TensorFlow. We will explore now the parts of framework, which is going to help developer with tools to debug the code. So in this slide, TensorFlow debugging, so we will be exploring about different debugging techniques available in TensorFlow. TensorFlow has got some niche debugging techniques. They are 1. Convert tensors to numpy array and print. 2. TensorFlow is fastidious about types and shapes. Check that types or shapes of all tensors match. 3. TensorFlow API is less mature than NumPy API. Many advanced NumPy operations, example complicated array slicing, not supported yet. 4. If you are stuck, try making a pure NumPy implementation of forward computation. 5. Then look for analog of each NumPy function in TensorFlow API. 6. Use tf.interactive session to experiment in shell and trial and error works. So this was a classic debugging technique used by developers till they become familiar with TensorFlow debuggers. Following our debugging assumptions, every TensorFlow developer needs to remember while programming. Point number 1. Assertion and print statements that know the actual value of the tensor should be added to the graph. Point number 2. Assertion operations is not needed for computing the output. The solution in TensorFlow for this is, I'll read the code. Assert underscore OP is equal to tf.assert within round braces tf.reduce underscore all of x greater than 0, square bracket of x close the round braces. X is equal to tf.width underscore dependencies within round braces within square bracket assert underscore OP, x close the round braces. With tf.control underscore dependencies within round braces within square brackets tf.assert underscore equal within round braces x, y close the round braces close the square bracket close the round braces colon x is equal to tf.identity of x. Printing an identity option that can be placed in the graph. X is equal to tf.print of x, within square bracket tf.argmax of x close the square bracket, within quotes argmax of x is equal to close the quotes, close the round braces. So these are the things that TensorFlow developer needs to remember while programming. You have a TensorFlow built-in debugger, also known as TF-DBG. It is a specialized debugger for TensorFlow. It lets you view the internal structure and states of running TensorFlow graphs during training and inference, which is difficult to debug with general-purpose debuggers such as Python PDB due to TensorFlow's computational graph parallel. TF-DBG can be used to debug problems that occur in the middle of the training, example, inference values. TF-DBG can be used to run n steps or until some tensor values match a given filter. Point number 2, TF-DBG can be used to print values of tensors and trace them to Python code. And number 3, TF.db can be used to display information about computational graph. To add support for TF.db in our example, all that is needed is to add the following lines of code and wrap the session object with a debugger wrapper. Let me read the code. From TensorFlow.python.debug, import local CLI debug wrapper session. Ses is equal to local CLI debugger wrapper session within round braces ses. From TensorFlow.python.debug, import local CLI debug hook. Ex is equal to experiment.experiment within round braces train underscore monitors is equal to local CLI debug hook. Close the round, square bracket, close the round. The TensorBoard debug plugin code which you saw earlier is debugger wrapper for session object, which helps you in monitoring the graph. The TensorBoard debugger plugin is a GUI of TF.dbg. It offers features such as inspection of the computation graph, the real-time visualization of TensorFlow, continuation to tensor, and conditional breakpoints, and tying tensors to the graph construction source code, all in the browser environment. Coming to Python native debuggers, there are many debuggers from Python, PDB, IPDB, PUDB, etc. You can enable them by pressing example import PDB semicolon IPDB dot set underscore trace. This code segment, you can place it wherever you want to debug. For further details on TensorFlow debug, you can visit the website https://tensorflow.org/guide/debugger, and GitHub repository URL is https://github.com/tensorflow/tensorboard/blog. I am recording the URLs in the description below. Now we will explore the visual aspect of TensorFlow framework, that is TensorBoard. TensorBoard is a dashboard provided by TensorFlow team. TensorFlow has some neat built-in visualization tools called TensorBoard. TensorBoard is a web interface for monitoring training. TensorBoard can be used for remote work but needs elaborate setup when TensorFlow is running remotely. So I would suggest you to check out for your projects while implementing the code on cloud. I've listed down the links for setup of transport down below in the description. To start the TensorBoard service, use the command TensorBoard --log directory path to the model directory --port and the port value, and point your web browser to the address that gets printed. So from there in the browser you can start monitoring the TensorFlow's computational graph. You can see the main graph as well as the auxiliary nodes as a sample demo that we had run in our cloud, and you can see how the graph can be monitored. Coming to the loss functions. Loss functions are very important to machine learning algorithms. They measure the distance between the model outputs and the target, that is truth values. In this recipe, we show various loss function implementation in TensorFlow. Evaluating outcomes in TensorFlow depends on specifying a loss function. A loss function tells TensorFlow how good or bad the predictions are compared to the desired result. In most cases, we'll have a set of data and a target on which to train our algorithm. The loss functions compares the target to the prediction and gives a numerical distance between the two. So let's see the code. Log its is equal to df.maximal of x, w plus b. Hypothesis is equal to tf.nn.softmax of log its, and when we check for the cross-country entropy cost or loss is equal to tf.reduce underscore mean within round braces tf.nn.softmax underscore cross underscore entropy underscore width underscore log its colon log its comma labels is equal to y underscore 1 underscore hot. According to the different problem types above, there are several reasons why we might prefer one combination over another. The parameter which minimizes loss function, that is delta L divided by delta W jk. So if you are using a computational graph which is of binary classification and you use a sigma node activation, then you have equation of number 1, that is delta L divided by delta Wjk is equal to within round versus tk minus yk multiplied by yk into 1 minus yk into xj. Then you need to use a loss function of mean square error. And if the equation is of type 2, that is delta L divided by delta Wjk is equal to tk minus yk divided by yk into 1 minus yk whole multiplied by yk into 1 minus yk into xj is equal to tk minus yk into xj. So that time you need to use multi-classification softmax function. Similarly, if you go through the other table, you can understand that each one has to be chosen depending on the situation that is required for that particular problem definition. As described above, cross entropy is usually used for probabilistic output. Mean squared error is usually used for regression. Using mean squared error and the softmax sigma function together is not recommended, as this may lead to very slow learning.
Optimizers. The optimizers are used for improving speed and performance for training a specific model. Optimization in TensorFlow has following. 1. Common optimization methods are implemented in various subclasses of tf.train.optimizer. Some of the popularly used optimizers are ADA Delta Optimizer, ADA Grad Optimizer, Momentum Optimizer, Atom Optimizer. By default, all trainable variables are optimized. Point number 3. Minimize cost, returns an operation that performs one training step. Let me read the sample optimizer code. Optimizer is equal to gradient descent optimizer within round brackets learning underscore rate is equal to 0.1. Optimizer underscore op is equal to optimizer dot minimize of cost. For I in range of training underscore steps colon is equal to sys dot run of optimizer underscore op. This is a sample code of gradient descent optimizer. The optimizers are the extended class which include added information to train a specific model. Optimizer class is initialized with given parameters, but is important to remember that no tensor is needed. Following are some of the popular optimizers in TensorFlow. Number 1 optimizer used in TensorFlow is stochastic gradient descent. SGD optimizer accepts learning rate decay. When training a model, it is often recommended to lower the learning rate as the training progresses. The function returns the decayed learning rate. It is computed as decayed underscore learning underscore rate is equal to learning underscore rate into decay underscore rate to the power of global underscore step divided by decay underscore steps. The second optimizer is momentum. Momentum helps stochastic gradient descent to navigate along the relevant directions, softens the oscillation in the irrelevant. It simply adds a fraction of the direction of the previous step to a current step. This achieves amplification of speed in the correct direction and softens the oscillation in wrong direction. This fraction is usually in the range of 0 to 1. It also makes sense to use adaptive momentum. As you can see in the diagram, momentum step, actual step and the gradient step, you can generate the update rule for the momentum. Coming to the third one, Nesterov momentum. Nesterov momentum is also known as Nesterov's accelerated gradient, abbreviated as NAG, invented by Nesterov in 1983. It is a first order optimization method which is proven to have better convergence rate guaranteed than gradient descent for general convex function with Lipschitz continuous derivatives, that is order of 1 by t2 versus order of 1 by t. Nesterov accelerated gradient NAG is a first order optimization method to improve stability and convergence of regular gradient descent. Recently it was shown that
NAG could be computed by the following update rules. Vt is equal to mu t minus 1 into Vt minus 1 minus Qt minus 1 delta f of theta minus 1 plus mu t minus 1. Vt minus 1 is the first statement. Theta t is equal to theta t minus 1 plus Vt. So we can substitute the above value of Vt in the second statement. Where theta t are the model parameters, Vt the velocity, mu t is a set of 0, 1, the momentum decay coefficient, and Qt is greater than 0 is the learning rate at iteration t. F of theta is the objective function, and delta f theta prime is the shorthand notation for the gradient delta f theta, and delta theta given that theta is equal to theta prime. These equations have a form similar to standard momentum updates. Vt is equal to mu t minus 1 into Vt minus 1 minus Qt minus 1 delta f of theta t minus 1. This is the statement 3 or equation 3. Theta t is equal to theta t minus 1 plus Vt is expression or equation 4 is equal to theta t minus 1 plus ut minus 1 Vt minus 1 minus Qt minus 1 delta f of theta t minus 1 is equation 5, and differ only in the evaluation point of the gradient at each iteration. This important difference thought to counterbalance too high velocities by peaking ahead actual objective values in the candidate search direction results in significantly improved recurrent neural networks performance on a number of tasks. While optimization path taken by momentum exhibits large oscillations along the high curvature vertical direction, Nestrov's accelerated gradient is able to avoid these oscillations completely, confirming the intuition that it is much more effective and momentum decelerating over the course of multiple iterations. That is, this results in improved stability. Also note that there is little difference in the progress of both Nestrov's accelerated gradient and momentum along the horizontal direction of the quadratic due to the fact that gradient changes only very slowly along this direction. Nestrov momentum can be defined with the following update rule. Vt is equal to beta Vt minus 1 plus alpha of delta w L within round braces w minus beta Vt minus 1 comma x comma y, where w is equal to w minus Vt. So you can see in the figure momentum step and the actual step. The momentum steps looks ahead, and that is the gradient step, a bit different from the original. Now coming to the ADA grade. ADA grade is an optimizer with parameter specific learning rates which are adapted relative to how frequently a parameter gets updated during training. The more updates a parameter receives, the smaller the updates. It is recommended to leave the parameters of this optimizer at their default values. ADA grade is an algorithm for gradient based optimization that does just this. It adapts the learning rate. ADA grade is an algorithm for gradient based optimization that does just this. It adapts the learning rate to a parameters performing smaller updates, that is, low learning rates for parameters associated with frequently occurring features, and larger updates, that is, high learning rates for parameters associated with infrequent features. For this reason, it is well suited for dealing with sparse data. Coming to the ADA delta optimizer. ADA delta is an extension of ADA grade that seeks to reduce its aggressive monotonically decreasing learning rate. Instead of accumulating all past squared gradients, ADA delta restricts the window of accumulated past gradients to some fixed size w. Instead of inefficiently storing w previous squared gradients, the sum of gradients is recursively defined as decaying average of all past squared gradients. The ADA delta update rule is as follows. Delta theta is equal to minus RMS within square bracket delta theta t minus 1 whole divided by RMS of gt multiplied by gt. I'll repeat. Delta theta is equal to
minus of RMS of delta theta t minus 1 divided by RMS of g of t whole multiplied by gt. That is theta t plus 1 is equal to theta t plus delta theta t. At delta, we do not even need to set a default learning rate as it has been eliminated from the update rule. Now let's move to RMS prop optimizer. RMS prop optimizer is similar to the gradient descent algorithm with momentum. The RMS prop optimizer restricts the oscillation in vertical direction. Therefore, we can increase our learning rate and our algorithm could take larger steps in the horizontal direction, converging faster. The value of momentum is denoted by E within square bracket g square close the square bracket t and is usually set to 0.9. Maintain a moving or discounted average of the square of gradients. Divide gradient by the root of this average. Sometimes the value of E within square bracket g square close the square bracket into t would be easily close to 0. Then the value of our weights could blow up. To prevent the gradients from blowing up, we include a parameter epsilon in the denominator which sets it to a small value, where E of g is the moving average of squared gradients and g square t is the gradient of cost function with respect to the weight, n is the learning rate, beta is the moving average parameter which default value is 0.9. So the update rule will be for RMS prop will be E within square bracket g square close the square bracket t is equal to 0.9 E of within square bracket g square close the square bracket t minus 1 plus 0.1 g square t. Now theta t plus 1 is equal to theta t minus n divided by square root of E within square bracket g square of t plus epsilon whole multiplied by gt. Addon is an optimization algorithm that can be used instead of classical stochastic gradient descent procedure to update network weights iterative based in training data. The method computes individual adaptive learning rates for different parameters from estimates of first and second moments of the gradients. The name Addon is derived from adaptive moment estimation. Our method is designed to combine the advantages of two recent popular methods, AdaGrid, invented by Duchy et al. In 2011, which works well in sparse gradients, and RMS props, invented by Tillman and Hilton in 2012, which works well in online and non-stationary settings. Addon, in short, for adaptive moment estimation, is the ith component of the teach step is given by learning rate divided by square root of exponential underscore decay of average of squared gradients of ith component plus epsilon whole multiplied by exponential of decay underscore average underscore of gradients I. Here the parameters are exponential underscore decay underscore average of grades underscore I is an exponential decay average of the ith components of all the gradients calculated. Gradient I, actually both exp underscore decay underscore average of grades of I and exponential decay underscore average of squared grades underscore I are also corrected to account for a bias towards theta. In Addon, the update rule for individual ways is to scale their gradients inversely proportional to a scaled L2 norm of their individual current and past gradients. When introducing the algorithm, the authors list the attractive benefits of using Addon on non-convex optimization problems as follows: straightforward to implement, computationally efficient, little memory requirements, invariant to diagonal rescale of gradients, well suited for problems that are large in terms of data and or parameters, appropriate for non-stationary objectives, appropriate for problems with very noise or sparse gradients. Hyperparameters have intuitive interpretation and typically require little tuning. So these were some of the benefits of using Addons. Addon Max is a variant of Addon based on infinity norm. In our Addon update rule scales the gradient inversely proportional to the L2 norm of the past gradients Vt-1 and the current gradient term Gt whole square. Instead of this, we generalize the update rule to IP norm, that is ut is equal to beta 2 to infinity Vt-1 plus 1 minus beta 2 to infinity, close the bracket, Gt raised to infinity is equal to max of beta 2 dot Vt-1 comma absolute of Gt. Putting p to the infinity, ut is used to define the infinity norm constant instead of Vt. So this is the add max update rule. SMOR MS3, SMOR MS3 or SMORMS3 is a hybrid of RMS prop, which is perhaps trying to estimate a safe and optimal distance based on curvature, or perhaps just normalizing the stepwise parameter space, and a part of Lee-Kuhn's method, which is choosing a learning rate based on how noisy the gradient is. I'll be giving you the paper description or paper URL in the description below. Now moving to the layers. The simplest form of artificial neural network, also known as perceptron, it is also called single-layer perceptron. Rosenbladt's single-layer perceptron is one of the earliest models for learning. In particular, the perceptron implements the following function to solve the classification problem. That is, y cap is equal to f of sum of I12 d, where weights wx plus b. Where f is a nonlinear function, d is the number of features or dimensionality of the problem. As we can see, the changing values of wi and b gives us different functions. Thus, it defines a collection of functions. Target of learning is to find out the w and b that best capture the input-output relationship, as you can see in the diagram of the slide, where x0 action from a neuron supplies with the w0, synapse with w0 x0, similarly w1 x1, w2 x2. The summation of all this inside the cell body and an activation function is called to get the output axon with the value of function f, summation of wi xi plus b. The multi-layer perceptron contains many perceptrons that are organized into layers. The multi-layer perceptron consists of 3 or more layers, an input and an output with 1 or more hidden layers of non-linearly activating nodes. Since multilinear perceptrons are fully connected, each node in one layer connects with a certain weight to every node in the following layer. Every neuron in it has the weight and bias parameters. It gets the data from every input and performs some calculation. This is what makes it fully connected layer. TensorFlow's tf.layers package allows you to formulate all this in just one line of code, and all you need to provide is the input and the size of the layer. Let me read the code for layers. Output is equal to tf.layers.dense within round bracket. Input is equal to input, comma, units is equal to labels underscore size. A large range of layers types are there: fully connected, convolution layer, pooling layer, flatten layer, batch normalization layer, dropout layer, and convolution transpose layer. Now we'll discuss about estimators. Estimators encapsulate the following actions, namely 1. Training, 2. Evaluation, 3. Prediction, 4. Export for serving. All estimators, whether pre-made or custom, are classes based on the tf.estimators.estimator class. Estimators simplify sharing implementations between model developers. It is generally much easier to create models with estimators than with the low-level transferable APIs. Estimators are themselves built on tf.keras layers, which simplifies the customization. Estimators build the graph for you. Estimators provide a safe distributing training loop that contains how and when to build the graph, when to initialize the variables, when to load the data, when to handle exceptions, how to create checkpoint files, and when to recover from failures, and how to recover from failures, when to save summaries for TensorBoard. When writing an application with estimators, you must separate the data input pipeline from the model. This separation simplifies experiments with different data sets. Estimators are ready for training, evaluating, and exporting the model on a single machine. For production usages and models with large amounts of training data, utilities for distributed execution are also provided together with estimators, which takes the advantage of TensorFlow's distributed training support. The core of distributed execution support is the experiment class, which groups the estimator with two input functions for training and evaluation. TensorFlow estimators simplify or automate all but the debugging steps. Estimators gives the practitioner confidence that when debugging not a number or poor quality, these problems arise either from their choice of hyperparameters or their choice of features. The estimators framework made it easy to implement new estimators and experiment with new model architectures such as multiple objective learning to accommodate specific product needs. Input functions are used for passing input data to the model for training and evaluation. Feature columns are specifications for how the model should interpret the input data. In the left figure, you can see that custom estimators are widely used compared to the other built-in estimators. The core of Estimator API has stayed stable. We can still create an estimator as follows. Return tf.estimator.estimator within round braces. Model fn is equal to model fn, config is equal to config, params is equal to params, where model fn is the function initializing the model. This function is represented and fully defined by the estimator spec object, which knows how to generate all outputs, how to train and how to evaluate the model. This model function is still agnostic to how you implement the architecture. You can use tf.layers or other libraries to implement your model architecture. Config is a run config object specifying how to run the estimator. It knows where to save the checkpoints, how many times to save the checkpoints, when to log, etc. Params is an object holding the hyperparameters of the model. After creating the estimator, we can train it using the train and evaluate function. That is tf.estimator.train and evaluate within curly braces model estimator, train spec, eval spec, close the round braces. By using the above estimator API, it also sets up default logging, checking, point saving, which we can visualize with TensorBoard. Here you can see a small snapshot of estimator being plotted in the TensorBoard. With tf.estimator.train and evaluate, you can run the same code both locally and distributed in the cloud on different devices using different cluster configuration and get the consistent results without making any code changes. Now let's discuss about eager execution and deferred execution. TensorFlow's eager execution is an imperative programming environment that evaluates operations immediately without building graphs. Operations return concrete values instead of constructing a computational graph to run later. Eager execution is a flexible machine learning platform for research and experimentation, providing number one, an intuitive interface, that is, structure your code naturally and use Python data structures, quickly iterative on small models and small data. Number two, easier debugging, that is, call operations directly to inspect running models and test changes. Use standard Python debugging tools for immediate error reporting. Point number three, natural control flow. Use Python control flow instead of graph control flow, simplifying the specification of dynamic models. So, eager execution supports most TensorFlow operations and GPU acceleration. So, let's see the code. From __future __ import absolute import, division, print function. Import TensorFlow as TF. tf.enable _eager execution. So this part of the code enables the eager execution. Most TensorFlow operations work during eager execution, but there are some things to keep in mind. Number one, use tf.data for input processing instead of queues. It's faster and easier. Number 2, use object-oriented layer APIs like tf.keras.layers and tf.keras.model, since they have explicit storage for variables. Once eager execution is enabled with tf.enable_eager_execution, it cannot be turned off. To move to graph execution, you need to start a new Python session. So let's see the code. tf.enable_eager_execution and a is equal to tf.constant of within square brackets 1, 2, close the square bracket, open another square bracket 3, 4, close the square bracket, close the square bracket, and then print a. You get tf.tensor within square bracket the contents of the tensor, that is square bracket 1, 2, square bracket 3, 4, and the shape is equal to 2, 2, and d type is equal to int32. In eager execution, output of an operation will be actual value, not the tensor. Now moving to the graph mode. TensorFlow follows a deferred execution methodology. We initially set up a graph of how the computation should take place and later start the execution. Execution here refers to pumping in data continuously in batches. More about that in later. To the computation graph while tweaking the weights. TensorFlow uses a data flow graph to represent the computation in terms of the dependencies between individual operations expressed as nodes in a data flow graph. This leads to a low-level programming model in which the developer first defines the data flow graph and then creates a TensorFlow session to run parts of the graph across a set of local and remote devices. TensorFlow uses a deferred execution methodology when developer first sets up a graph of operations, constants and variables, then later starts the execution, pumping in data continuously or in a batch. The key concept of TensorFlow is that it's a way to defer the execution of a complex calculation, defining a flow of constants, variables and operations, managing tensor values. So you can see in the computational graph figure how the tensors flow from one point to the other across the computational graph. Data flow has several advantages that TensorFlow leverages when executing the programs. Point number 1, parallelism. By using explicit edges to represent dependencies between operations, it is easy for the system to identify operations that can execute in parallel. Distributed execution. By using explicit edges to represent the values that flow between operations, it is possible for TensorFlow to partition your program across multiple devices, CPUs, GPUs and TPUs, attached to different machines. TensorFlow inserts the necessary communication and coordination between devices. Point number 3, compilation. TensorFlow's XLA compiler can use the information in your data flow graph to generate faster code, for example by fusing together adjacent operations. Point number 4, portability. The data flow graph is a language-independent representation of the code in your model. You can build a data flow graph in Python, store it in a save model and restore it in C++ program for low latency inference. Here you can see the graphical representation of how the data flow graph happens for a SGD trainer. Coming to autograph. Autograph helps you write complicated graph code using normal Python. Behind the scenes, Autograph automatically transforms your code into the equivalent TensorFlow graph code. Autograph already supports much of the Python language and that coverage continues to grow. So let us read the autograph code. From __future_ import division, print function, absolute import. Import TensorFlow as TF. Layers is equal to tf.keras.layers. From TensorFlow import contrib. Autograph is equal to contrib.autograph. Import numpy as np. Import matplotlib.pyplot as plt. Autograph works in both eager and graph execution environments. Autograph will convert much of the Python language into equivalent TensorFlow graph building code. As you can see, the earlier code I read had mixture of both Python code as well as TensorFlow code. Autograph bridges the gap between eager execution and graphs. Autograph takes in your eager style Python code and converts it into graph generating code. Autograph isn't just a collection of useful macros, It uses source code transformation to allow it to override any part of the Python language, including control flow, function application, and assignment, generating boilerplate code, and refactoring idiomatic Python to make it easy to turn into graphs. Autograph lets you use your dynamic and flow control heavy models on accelerator hardware like GPUs and cloud TPUs, which is necessary when training large models on lots of data. With improvements of Autograph in the future, you can expect to use Autograph to speed up hotspots by selectively turning eager code into graph fragments. Advantages of graph mode you can see in your slide. The eager mode has 6 lines of code, and the graph mode, it's automatically generated. It's performance effective, hence you get a generated code which is much suitable for execution performance. Now moving to tf.keras. Keras is a high-level API to build and train deep learning models. It is used for fast prototyping, advanced research, and production, with 3 key advantages, namely user-friendly. That is, Keras has simple, consistent interface optimized for common use cases. It provides clear and actionable feedback for user errors. Point number 2, modular and composable. That is, Keras models are made by connecting configurable building blocks together with few restrictions. Point number 3, easy to extend. That is, write custom building blocks to express new ideas for research, create new layers, loss functions, and develop state-of-the-art models. Now to the last slide, we'll touch upon the TensorFlow 2.0 new features. TensorFlow 2.0 has made a lot of news recently, so I'll not be exploring much on this because it's in the alpha state. So Transfer 2.0 will focus on simplicity and ease of use, featuring updates like easy model building with Keras and eager execution, robust model deployment in production on any platform, powerful experimentation for research, simplifying the API by cleaning up deprecated APIs and reducing duplication, removal of queue runners in favor of tf.data, removal of graph collections, changes to how variables are treated, moving and renaming of API symbols, distribution strategies for distributing training, export to save model. TensorFlow Federated TF is an open source framework for experimenting with machine learning and other computations on decentralized data. I have touched upon this during TensorFlow Addons, so you can go through that again. The last point is tf.contrib. TensorFlow's contrib module has grown beyond what can be maintained and supported in single repository. Larger projects are better maintained separately, while Google will incubate smaller extensions along with the main TensorFlow code. Consequently, as part of releasing TensorFlow 2.0, distributing tf.contrib is dropped. For more on the TensorFlow, we can visit tensorflow.org website. Thank you for listening.
Thank you for watching till the end. We will come back with a new programming techniques and tips about deep learning concepts in our next video. Please like and subscribe on video. Share the video with your friends. Please provide your feedback. Thank you and have a nice time.